Hello and welcome back to Unify Physics. In the previous class of classical mechanics, we started with the Lagrangian equations of motion, or Lagrangian mechanics. We discussed a few concepts. We saw what are constraints, we saw what we mean by a virtual work or virtual displacement and these things. We also discussed the equation of motion, right, called the Lagrange's equation. We solved a few problems. Today we are going to solve more problems. Okay? The first problem is of a double pendulum. And this was asked for the NET JRF exam in December 2011. Alright. So in this situation, a double pendulum. Okay, it's a double pendulum. What's a double pendulum? It consists of 2 point masses m. So it's one simple pendulum here and another simple pendulum attached to the bob of the first simple pendulum. That's called a double pendulum. Alright. Luckily here the masses of these both bobs are same and also these lengths are same, which makes life easier. Okay. So the kinetic energy of the pendulum, we are just asked to find the kinetic energy of the pendulum. Alright. So here's the situation. Now we know how to write the kinetic energy. We can write the total kinetic energy as T is equal to T1 plus T2, because these are kinetic energies. We can just add them, the total kinetic energy. Alright. And T1, it's quite easy. We have seen it in the case of a simple pendulum. Alright. We know that the tangential velocity here, there is no radial movement. There is no radial movement. It has only tangential movement. Right. The tangential velocity, we know that it's equal to, let me write it as V tangential or something. V tangential is equal to L theta dot. Am I right? It's like V is equal to R omega, that thing. So the kinetic energy T1 is equal to half m L square theta dot square. Okay, no problem there. Okay. But we need to be a bit more careful to find T2. Okay, so let's start with the transformation equations. Let's give the coordinates of the first mass as x1 and y1. Okay, and the coordinates of the second mass we'll call x2 and y2. Alright, and as you see, we can take theta 1 and theta 2 as the generalized coordinates. That's enough. Alright. So let's look at x1. Let's write down the transformation equations. Okay. So we see that x1, as you see, x1 is this length. Alright. We can take this line as the y-axis. Alright. Along this line, we'll say x equal to 0. Alright. So x1 is this length, and that is L sine theta 1. Okay, and y1, what's y1? y1 is this length. Am I right? So that length, so that is equal to L cos theta 1. Okay, now you could easily find T1 also using this half m x1 dot square plus y1 dot square. All right, and you'll get back this equation. Okay, no problem there. Okay, what about x2? x2, as I said, it's this length. This is x2. Okay, we see that x2 is equal, and we know that this small length, this is L sine theta 2, right? This is L sine theta 2, and this length was L sine theta 1, right? This length, this is L sine theta 1, this is L sine theta 2. So we see that x2 can be written as L sine theta 1 plus L sine theta 2. Okay, similarly, y2 can be written as, right? y2 is this length. Okay, so it's this length plus this length, and this length we already know is L cos theta 1. So this is L cos theta 1 plus, and what's this length? That is L cos theta 2. Okay, now we have written down the transformation equations. Okay, we have fixed the generalized coordinates and we have written down the transformation equations. Alright, now it's just a matter of calculation. We can write T2, the kinetic energy of the second mass, as half m x2 dot square plus y2 dot square. Alright, and now you find x2 dot from here, y2 dot from here, square them. Okay, so I'll write it here. We can write T is equal to half m x2 dot square plus y2 dot square. So we just substitute for x2 and y2 in here, and what do we get? We get is equal to half ml square. Okay, because we are it's half m, there's a half m here, and this l square can be pulled outside, so we take half ml square. Okay, so it's half ml square. All right, and x2 dot square, you can write it as cos theta 1 dot plus cos theta 2 dot whole square. Okay, that would be x2 dot square. Okay, that would be x2 dot square. Okay, x2 dot square. Just take the time derivative of this and square. Okay, and what's y2 dot square? Plus what we have here is minus sine theta 1 dot minus sine theta 2 dot whole square. Okay, this minus comes because we are taking derivative of cosine. All right, y2 dot. When we take y2 dot here, okay, as you see, y2 dot, right, from here we see that y2 dot is equal to minus L sine theta 1 dot minus L sine theta 2 dot. Okay, that's what we have written here. Right, now you square and add, so we'll say that this is equal to half ml square. So this is only t2. Okay, half ml square cos square theta 1 dot square plus cos square theta 2 dot square, right, plus 2 cos theta 1 cos theta 1 dot theta 2 dot. Okay, similarly we square this thing, we get plus sine square theta 1 dot square plus sine square theta 2 dot square. Okay, again there's a plus here because it's 2ab. All right, 2 sine theta 1 sine theta 1 dot theta 2 dot. Okay, we have just squared and added. Now this is equal to half ml square. See, we can combine this. Cos square theta plus sine square theta is 1. So this is 2 cos square theta 1 dot square multiplied by cos square theta 1 plus sine square theta 1. So that's equal to theta 1 dot square plus, similarly from here we get theta 2 dot square. Just add this. Okay, plus, okay, this thing we can write as twice theta 1 dot theta 2 dot, and we have got here cos theta 1 cos theta 2 plus sin theta 1 sin theta 2, and we know that that's equal to cos theta 1 minus theta 2. Okay, if you are not, we can just, because we know that cos theta 1 minus theta 2 can be written as cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. Okay, the trigonometric identity, you might be familiar with it already. Okay, so this is T2, right, and we need to find T, the total kinetic energy, that's equal to T1 plus T2. Okay, so T1 we can take from here, it's half ml square theta dot square, theta 1 dot square actually. Okay, theta 1, so that's equal to half, there's a half ml square over there. Okay, there's a theta 1 dot square, we can combine it with this theta 1 dot square, so it becomes 2 theta 1 dot square plus theta 2 dot square plus 2 theta 1 dot theta 2 dot cos theta 1 minus theta 2. Okay, that's the answer for the total kinetic energy. I think we have it in our options. Okay, 2 theta 1 dot square plus theta 2 dot square plus 2 theta 1 dot theta 2 dot cos theta 1 minus theta 2. So the option B is the correct answer. Okay, so we have only found the kinetic energy here. All right, and as an exercise, okay, as a practice, as an exercise, you can okay, you can do this. Find, that's a homework. All right, find the Lagrangian and the Lagrange's equation of motion. And if you want more practice, all right, if you want more practice, you can do the general case. Okay, you can do the general case. You can take this as L1, this as M1, this one as L2 and M2. Okay, if all these lengths and masses are different, you will get a rather complicated expression, and then you can see what happens when you put L1 equal to L2 and M1 equal to M2. Okay, so you can play around with that problem a little bit. That's a good exercise. Right. Now, here's the next problem. It's a pendulum with a moving support. So the problem is given like this. A simple pendulum has a bob of mass m with a mass m1 at the moving support, right? So there's the support here, the pendulum support here, it's allowed to move along the x-axis. Okay? So it moves on a horizontal line in the vertical plane in which the pendulum oscillates. Find the Lagrangian and the Lagrange's equations of motion. Now how do we do this? We have to be careful here. This is a pendulum with moving support, right? And we have got two masses here. We have to take both into account. Okay. The first one, it's rather easy. Let's first write down the kinetic energy. Okay. So the first one we'll write as T1. T1, it has only 1 degree of freedom. It can move only along the x-axis. So T1 is equal to half m x dot square. Right? Or yeah, we can write as half mx. T1 is equal to half mx dot square. All right. And what's T2? Before T2, we have to find the coordinates of these things. We'll call it as x1 and y1. Okay, x1 and y1. The coordinates are x1 and y1. So we have to be a bit careful here. Let's find what's x1. Right. X1 we see it's the sum of these two lengths. Okay, and what's this length? This length is nothing but x, the coordinate of the mass m1. Okay, so this whole length we can write it as x plus. Okay, x plus, and what's this? This is simply L sine theta. X plus L sine theta. Okay, that's it. We have done what needs to be done. What about y? Y1 is simple. It's simply this length, and it's L cos theta. Y1 is L cos theta. All right. Okay. Now we can find the kinetic energy T2. Let me write here. Okay. So T2 is equal to half m1. Okay, this is mass is m1. Sorry, this is T1. So we need to find T2. Okay, so that's half m x1 dot square plus y1 dot square. Okay, that's equal to half m x1 dot is equal to x dot plus x1 dot is x dot plus L cos theta theta dot. Okay, that's x1 dot square plus y1 dot square is L minus L. Okay, so that becomes plus y1 dot, that is minus L sin theta theta dot square. Okay, that's T2. Now it's a matter of simplifying this. So it's half m. What do we get from here? We can write it as x dot square plus L square cos square theta theta dot square. All right, plus 2x dot L cos theta theta dot, right, plus L square sin square theta theta dot square. Can we further simplify it? Yes, if you take this L square theta dot square outside here, okay, this is cos square theta plus sin square theta. So T2 is half m, okay, x dot square plus 2x dot L cos theta theta dot, all right, and x dot square plus 2x dot L cos theta theta dot, and this together plus L square theta dot square. Okay, that is T2. Okay, we have got T1 as half m1 x dot square and T2 as this. Okay, so if you look here, there are two generalized coordinates. One is x and the other one is theta. You need these two coordinates in order to completely specify the configuration of the system. Okay, all right. So we just take the total kinetic energy. T is equal to T1 plus T2. For T1 we had half m1 x dot square, and for T2 we got half m x dot square plus 2x dot L cos theta theta dot plus L square theta dot square. Okay, that's the kinetic energy. We also need the potential energy. All right. Now, as I said, choice of a reference point. It doesn't change your result, but it can make things easier. All right. If you choose wisely, it can make things easier. All right. So if you look here, if you take this line as the potential energy 0, we can take this line as the 0 potential energy, or this as the reference point. So the potential energy for the mass m1 will be 0, and you will have only a non-zero potential energy for the mass m. Okay, that makes it easier, right? So if we take this as the reference line, then potential energy of mass m1, that becomes 0. Okay, potential energy of mass m2 or mass m, that becomes, what's the potential energy of mass? That's minus m g, and what's this height? It is L cos theta, minus mg L cos theta. Okay. All right. So that's the total potential energy also, because the first one is 0. Now we can write down the Lagrangian. The Lagrangian is equal to half m1 x dot square plus half m x dot square, okay, plus 2 x dot L cos theta theta dot plus L square theta dot square. All right, and minus, it's t minus v, so it becomes plus mgl cos theta. Okay, if you don't remember, L is equal to t minus v. Okay, we have got the Lagrangian. Now we just have to find the equations of motion. All right, so first let's find the equation for x, Lagrange's equation, all right, for x, the coordinate x. As we said earlier, each coordinate has its own equation. All right, so this equation we can write as d by dt. Okay, so if you look here, you see that there are no x. There is no x in this Lagrangian. All right, there is no x in this Lagrangian. X does not feature in this Lagrangian. All right, so it is independent of x. There is a word for it. We say that x is cyclic. Okay, or x is a cyclic coordinate. X is a cyclic coordinate. All right, or the Lagrangian is cyclic in x. We can also say that the Lagrangian is cyclic in x. Okay, x does not feature. The Lagrangian is independent of x. All right, so dou L by dou x is 0. We only have to find dou L by dou x dot, which should be m1 x dot. All right, and mx dot from here. Okay, and 2L cos theta theta dot from here. That would be dou L by dou x dot. Okay, so d by dt of dou L by dou x dot, that becomes m1 x dot plus mx dot plus ml cos theta theta dot, that's equal to 0. Okay, so you see that the Lagrangian does not feature the coordinate x. Then we get a conservation law. There is some quantity which does not change with time. Okay, there is a conserved quantity, right? There is a conserved quantity which does not change with time. Okay, so for future problems we will just introduce this concept. If the Lagrangian is cyclic in some of the coordinates, then the corresponding conjugate momentum is conserved. All right, so if you have the coordinate q, dou L by dou q dot, okay, we can write it as p. That's known as the momentum. We call this as the momentum conjugate to the coordinate to q. Right, that's the momentum conjugate to q. Right, so if the Lagrangian does not feature q, we immediately get a conservation theorem. Right, we immediately get a conservation law. Right? If q does not appear in the Lagrange's equation says that d by dt of dou L by dou q dot for just one coordinate. All right, or let's say ith coordinate, minus dou L by dou q I is equal to 0. Right, now if the Lagrangian is independent of qi, then this term is 0. Right, if the Lagrangian is independent of qi, or if the Lagrangian is cyclic in qi, or if qi is a cyclic coordinate, then this term is 0. So we get immediately a conservation law, d by dt of dou L by dou qi dot is equal to 0. That's the same thing that we have got here. Right, we saw that the Lagrangian does not feature x, and we see that there is a conserved quantity. There exists a conserved quantity. Okay, in fact, this is a special case of what we will discuss later as the Noether's theorem. Noether's theorem. Right? Noether's theorem tells us about the relationship between conservation laws and symmetry of the system. So when we say the Lagrangian does not depend on Q, it means that there is a symmetry. Right? You can change the coordinate Q and the Lagrangian does not change. That's called a symmetry. You do something to the system and the system does not change. All right? The Lagrangian does not change. That's called a symmetry. And this theorem says that whenever there is a symmetry, there is a conserved quantity. At least in classical physics, this is true. Whenever there is a symmetry, there is always a conserved quantity. All right? So here it's a cyclic. The coordinate being cyclic or Lagrangian being cyclic in a certain coordinate automatically means that there is a symmetry, because if you change that coordinate, right, the Lagrangian does not change, and that's called a symmetry. Right? So that was a slight deviation from what we were discussing. I just wanted to say, so there is some conserved quantity here. There is some conserved quantity here. Okay. Now we can just simplify this. You can take the derivative and the final result would be m plus m1 x double dot plus ml cos theta theta double dot minus ml sin theta theta dot square is equal to 0. Okay. This is the equation for x. We can find the equation for theta also. The equation of motion for theta. Okay. So here we see that it depends on theta. All right. Theta is not cyclic. So we need to find dou L by dou theta dot and dou L by dou theta and then combine it in the form of this Lagrange's equation. All right. So you can check this equation becomes dou L, if you take dou L by dou theta and take d by dt of it, you say d by dt of ml square theta dot plus ml cos theta x dot plus mx dot L sin theta theta dot plus mg L sin theta is equal to 0. And now if you take the derivative here, you will see that you will get another minus mx dot. So if you take the time derivative, all right, you see that there is a term minus m x dot sin theta theta dot, and they will get cancelled. You will have to use the product rule there. So you just simplify this and you will get the final result as ml square theta dot plus ml cos theta x double dot. So ml square theta double dot. You can check this, all right, plus mg L sin theta is equal to 0. All right. So we see that these problems are not very difficult to do if we just have the correct starting point. All right. The rest is just differentiating with respect to time or with respect to certain coordinate. If you are careful, if you do it carefully, there is no reason to make a mistake. All right. These are easy problems. All right. The only thing that you need practice with, I think, you need to practice newly is to find out the most suitable generalized coordinates. All right. And also you have to get the correct transformation equation. Most of the times you find the transformation equations just from the geometry. All right. In this, as in this case, all right, some trigonometric relations or some geometric relations will help you obtain the transformation equations. Now once you have obtained the transformation equations, you can find the kinetic energy. Right, you can find the kinetic energy, you can find the potential energy, and these things are easily calculated. All right, if there are a number of masses, for example, the total kinetic energy is just the sum of all the kinetic energies, and total potential energy is also just the sum of all the potential energies. Okay. All right. The next problem we are dealing with is known as the spherical pendulum. Okay. So a spherical pendulum that is free to swing the entire solid angle is called a simple pendulum. It's a simple pendulum, right? It's a simple pendulum, but simple pendulum can only move like this, but this can go the entire solid angle, right? So find the differential equations. There are 2 degrees of freedom, as you might notice, because the length of the string is fixed. It does not change. Okay, there is no radial movement, so it can move, it can have 2 degrees of freedom. Find the differential equations of motion of a spherical pendulum using Lagrange's method. Also show that the angular momentum about a vertical axis through the point of support is a constant of motion. So in short, we are asked to find the Lagrange's equation, and we are asked to identify a constant of motion. Okay? So we already saw a trick to identify the constant of motion. If certain coordinates are cyclic, right? If certain coordinates do not appear in the Lagrangian, then the momentum conjugate to that particular coordinate will be a conserved quantity. Okay? That's what we need to find here. Okay, so how do we go about doing this one? All right. So the spherical thing, we can write it like this. All right. We can draw it like this, and this angle is phi, and this is psi, and we call this angle theta. All right. Theta is the angle made with respect to the z-axis. Okay. Phi is the angle made with respect to the x-axis. Okay. X, y, and z, and together that completely specifies the system. Okay. Now first we can start by writing down the transformation equations. Okay, or let's see, or there's a better way to do that. All right, rather than going through the transformation equations, that's also a way to do it. Okay, we look at the elementary lengths. What are the elementary lengths here? All right, what are the elementary quantities corresponding to elementary lengths here? All right, which means that for a small change in phi, what's an element of length corresponding to a small change in phi, d phi, for example. Okay, so we have already discussed this. We saw that for phi, I'll draw it in a slightly better manner here, or slightly different manner here. All right, so we have got this thing in the xy plane like this. Okay, so this angle is phi, and this line, okay, this line here we have got psi, and this angle is theta. Okay, the length of this line is L sine phi. Okay, because this is 90 degrees. Right, that's 90 degrees. All right, so we have got the length, this length. Okay, this length is L sine psi. Right, you can also write as L sine theta if you are talking only about the length. Okay, L sine theta. This length, the magnitude. All right, this length is L sine theta. Okay, L sine psi or L sine theta. You can see that they are the same when you take the magnitude. All right, so that's L sine theta. Okay, so the if you have that is L sine theta, this is phi. Okay, so if you have a small displacement, okay, if you have a small displacement d phi, right, d phi, the corresponding length element is this length multiplied by d phi, right, and this length is L sine theta, so that's L sine theta d phi. Okay, I hope that's clear. L sine theta d phi. All right, so this is the length element corresponding to a small change in the angle phi, okay, or a small angle d phi. Right? It's a length element corresponding to a small angle d phi. Okay, so the length element, or we can call it as the elementary lengths. Elementary lengths are, okay, we see that the elementary length here, okay, if the pendulum is here, then it is L sine theta d phi, and okay, and corresponding to a small change in theta, small change in the angle theta, or small change in the angle psi. Okay, you see that there's one more angle there, a small change in angle theta. Let's say there's a small change in angle theta, and the corresponding length element, if this is d theta, the corresponding elementary length is L d theta. Okay, so we have got and L d theta. All right, now you can easily find the corresponding velocity, just divide it by dt. Okay, so the velocities, or the tangential velocity components are L sine theta, let's say the velocities, okay, that is L sine theta phi dot, because if you divide it by dt, okay, d phi by dt, we write as phi dot, and there's one more L theta dot. Okay, so that's enough for us to identify the kinetic energy. Now we can find the kinetic energy. T is equal to half m L square theta dot square, the velocity square, okay, plus there is one more velocity, that's L square sine square theta phi dot square. Okay, that's not very difficult. Okay. Now we could also go to transformation equations between Cartesian and the spherical polar coordinates and do these calculations. Okay, you can do this calculation because we have the transformation equations. Okay, if you like to do it in the brute force way, okay, you know that x equal to L sine theta. If we take this as x, okay, we see that it's L sine theta cos phi or something, and y is equal to L sine theta sine phi, okay, y is equal to L sine theta sine phi, and z is equal to L cos theta. Alright, we can do these things and find t is equal to half mx dot square plus y dot square plus z dot square, okay, and in the end you will get this. Alright, you will get exactly this thing. Alright, we will have to use the condition that x square plus y square plus z square is a constant which is equal to L square. Alright, that's quite tedious, it takes a lot of time. Alright, the simpler way is to look at this and identify the elementary lengths. Okay, you identify the elementary lengths, okay, which means that I'll explain it, I'll try to explain it again. There are two angles, theta and phi. Okay, the question is, what are the elementary lengths associated with d theta and d phi? Alright, d theta and d phi, they represent two different changes of the configuration of the pendulum, or the position, or the orientation of the pendulum. Alright, so when theta changes by a small angle d theta, how much distance does the pendulum move? Okay, that's a question. Okay, alright, so that we can find easily. If it changes by a small angle d theta, this length is L, the corresponding length here, the change, the distance moved is L d theta. Okay, now if you have the distance moved, you need to find the velocity. You just divide it by dt and you get L theta dot. Okay, we already got one component of velocity. Okay, the other component is easily found as here. We see that this line, okay, this line is L sine theta. Okay, this length is L sine theta. Alright, now if there is a small change in the angle phi, let's call d phi, the corresponding length, okay, the corresponding distance moved is L sine theta d phi. And again, if you are doing it in a small time dt, the corresponding velocity would be L sine theta d phi by dt, or L sine theta phi dot. Okay, that's what we have here. The tangential velocities are L sine theta phi dot and L theta dot. Okay, now we can also remember it from this. We know that V is equal to R omega, right? V is equal to R omega. And we are assuming that the angles are angles are 90 degrees as in here. So V is equal to R omega. Alright, what's the R in this case? Corresponding to theta dot. If omega is theta dot, the corresponding R is L. Okay, the corresponding R is L. Okay, so we see that V is equal to L theta dot. Okay, and if phi dot is the angular velocity, the corresponding the corresponding radius is this thing. Okay, and that is L sine theta. Right, so V is equal to L sine theta phi dot. Okay, so this is how we identify the velocity components from here. Okay, and long story short, we get the kinetic energy like that. Okay. So it's good to practice this thing. You just look at this problem and identify the velocities immediately. In most cases, you can do that. You don't have to do all the transformation equations. Okay. Of course, when you practice, you can try using the transformation equations. But for an exam, okay, you should be able to write it down just by looking at it. In most cases, okay. Some cases you will have to go through the transformation equations. Okay. So we have to use these shortcuts whenever we can. Right, so that's the kinetic energy. And what's the potential energy? It's simply, we can again take this as the reference potential, okay, and that's minus mgl cos theta. So V is equal to minus mgl cos theta. Okay, that's it. We are done. We have got the Lagrangian. Right, Lagrangian is T minus V. Okay, so the Lagrangian is equal to T minus V. That's equal to half m L square theta dot square plus L square sine square theta phi dot square, right, minus mgl cos theta. Okay, we have to be, it's mgl minus mgl cos psi, alright, it's not cos theta, it's this angle, alright, we are taking this length, so it's minus mgl cos psi. Alright, we can write it in terms of theta because we chose theta as the generalized coordinate. I'm sorry. So V becomes minus mgl, okay, cos you see that this psi is actually 180 minus theta. Okay, so you see that V is equal to mgl cos theta. V is equal to mgl cos theta. Alright, we are taking the height from here. And that's equal to mgl cos theta. So it's that's equal to mgl cos theta. Alright, not minus mgl cos theta, but mgl cos theta. We have to be careful here because theta is taken from here and the angle shown here is psi. Okay, we'll write everything in terms of theta. That's easier. The height the height is actually L cos theta. We know that Z is equal to, or we can remember it like this. The potential energy is mgz, right? The height Z at a height Z, right? And Z is equal to L cos theta. So it becomes mgl cos theta. Okay, so there are different ways to do this. So that's correct. Okay, so it's plus mgl cos theta over there. Alright, no, minus is correct. Sorry again. Okay, so V is equal to mgl cos theta. Okay, so Lagrangian is T minus V. So it is equal to here it's a minus sign. Okay, I'm sorry. Alright. Okay. Alright, now we have written down the Lagrangian. Okay, we have to be careful, don't make this mistake again. Okay, alright, so we have got the Lagrangian. Now it's just a matter of finding dou L by dou theta dot, that's equal to ml square theta dot. Okay, and dou L by dou theta is equal to, you see that it's equal to ml square phi dot square sin theta cos theta plus mgl sin theta. Okay, that's dou L by dou theta. You can just check because there's a theta here and there's a theta over there. Alright, now we can also find dou L by dou phi dot. Dou L by dou phi dot is equal to ml square phi dot sin square theta. And what's dou L by dou phi? Dou L by dou phi, you see that there is no phi dependence in the Lagrangian. There is no phi dependence in the Lagrangian. So we can say the Lagrangian is cyclic in phi, or phi is a cyclic coordinate. Okay, so we say dou L by dou phi is 0. Okay, so immediately we get the conservation law here. We were asked to identify a conserved quantity, the conserved angular momentum. Okay, so we see that the equation corresponding to this is d by dt of dou L by dou phi dot is equal to 0. Okay, so we see that there is a conserved quantity dou L by dou phi dot. When you say quantity is conserved, it means that it does not change with time. So time derivative is 0. Okay, so the conserved quantity that we were asked to find, or the conserved angular momentum we were asked to find, is ml square phi dot sin square theta. Okay, or ml square sin square theta phi dot. We know that the angular momentum can be written as m r square omega. Okay, if you remember that. That's an angular momentum. Alright. So if the generalized coordinate is an angle, the corresponding conjugate momentum is angular momentum. Right? If the generalized coordinate you are talking about is an angle, then the corresponding conjugate momentum has dimensions of an angular momentum. The angular momentum is conserved. Okay. Alright, you can complete this problem by finding the equation for theta. Okay, just do d by dt of dou L by dou theta dot is equal to dou L by dou theta, and you also find for phi dot. Okay, I'll just write it down for you here. Alright, so for theta the equation becomes ml square theta double dot minus ml square phi dot square sin theta cos theta minus mgl sin theta is equal to 0. That's equation for theta. The equation for phi becomes, you can find the equation for phi. Alright, I'll just write it in this form. The equation for phi is a conservation equation, d by dt of ml square phi dot sin square theta is equal to 0. That's equation for phi. Okay. Alright, phi is called cyclic coordinate, etc. We discussed these things. Okay, and as I said, this is a special case of the Noether theorem, right? So one way to identify conserved quantities is to look for the cyclic coordinates. Is there some coordinates which does not appear in the Lagrangian? If so, then the corresponding conjugate momentum is conserved. All right. You can even make coordinate transformations, okay, to make some of the coordinates cyclic. Sometimes you will see that certain coordinate transformations can be made, and then some of the new coordinates can be made cyclic. All right. So that also can be done. Let's do another problem here for practice. Okay. All right. So we see that a particle of mass m is constrained to move on the inner surface of a cone of half angle alpha. Okay, half angle alpha. Half angle alpha with its apex on a table. Obtain its equation of motion in cylindrical coordinates r, phi, and z. Hence show that the angle phi is cyclic coordinate. Okay. So we are again asked to show that phi is a cyclic coordinate. We'll do that. We need to find the Lagrangian here, okay, and obtain the equation of motion. Okay. Now obtaining the equation of motion once we get the Lagrangian is just easy. All right. So here we see that the coordinate I think we'll use rho here because we'll use rho. Okay, rho, phi, and z. Okay. So we'll use cylindrical coordinates. Cylindrical coordinates. Okay. So what do we see here? What do we see here? We see that there is a constraint. The constraint is that this particle is confined to the inner surface of the cone. Okay, it's confined to the inner surface of the cone, right? Which means that there is a relation, right? Once z is fixed, once height is fixed, then rho is also fixed. Okay, this is rho. This distance is rho. Okay, so at a particular height, the rho is this distance rho at a particular height z. The distance rho is fixed by geometry of the cone. Okay, that's the idea. All right, it cannot be anywhere. It cannot take any random rho or z. All right, if the z at a particular height, it can have only a particular value for this rho. All right, and at this height the rho will be less like this. At this height the rho will be less like that. All right, how do we find this relation? Okay, we are given this alpha. Here the geometry of this cone, for example, is characterized by this alpha. Okay, so we can connect rho and z just by this. So if you see that tan alpha, if you look at it, tan alpha is equal to rho divided by z, or rho is equal to z tan alpha. If you like to eliminate z, then we can write z is equal to rho cot alpha. Okay, we have got the constraint equation. So we have only two independent coordinates, rho and phi. Okay, once we have rho, we can find z. All right, so these are z is not independent anymore. All right, so now we can write the kinetic energy. T is equal to half m. It's rho dot square again. Okay, rho itself. Okay, rho itself is a length, so you can the corresponding velocity is rho dot. All right, but again phi itself is not a length. Phi is not a length. Okay, phi is an angle. The corresponding length would be rho d phi. Am I right? Rho d phi. Okay, and the corresponding velocity would be rho phi dot or r omega as we usually speak about it. Okay, so it's rho dot square plus rho square phi dot square plus z dot square. All right, that's the kinetic energy because z is again a length. Okay, now we can write the constraint equation. We can put the constraint equation here, or we can substitute for z in terms of rho and alpha. So this becomes half m rho dot square plus rho square phi dot square plus rho dot square cot square alpha. Okay, alpha is a constant. Rho dot square cot square alpha. So now we can combine this. Rho dot square and 1 plus cot square alpha is cosecant square alpha. So this becomes half m rho square phi dot square plus rho dot square cosecant square alpha. Okay, that's the kinetic energy. Right, and what's the potential energy? What's the potential energy? We have to fix the reference point. We can fix this as the reference point. Okay, we can fix this as the reference point as 0. So z will determine the potential energy. All right, so we can say V is equal to mgz, and that's equal to mg rho cot alpha. Okay, v is equal to m0 cot alpha. So we have got the Lagrangian now. Okay, that's it. We are actually done. This is the difficult part. Okay, this is the part which is different in every problem. Okay, so L equal to t minus v, that's equal to half m rho square phi dot square plus rho dot square cosecant square alpha, okay, minus m0 cot alpha. Okay, now it's rather, so you see that there is cyclic coordinate. Identify the cyclic coordinate here. You see that there is one of the coordinates. Okay, the two coordinates, the generalized coordinates are rho and phi. We see that rho appears here, but we see that phi does not appear. Phi does not appear here. Okay, so immediately we know that the corresponding conjugate momentum, it has to be an angular momentum in this case, is a conserved quantity. So there is a conserved angular momentum. There is a conserved angular momentum. Okay, so you can find the equations of motion. All right, I think you can do it as an exercise. Okay, complete it. Find equations of motion for rho and phi. Okay, so you can just do this. Okay, it's d by dt dou L by dou rho dot, okay, minus dou L by dou rho equal to 0. That would be for rho. Similarly for phi. All right, for phi we see that it's a conserved quantity. We see that d by dt, because it does not depend on phi. Okay, d by dt of dou L by dou phi dot is equal to 0. Or we can say that d by dt of m rho square phi dot. Okay, because dou L by dou phi dot is m rho square phi dot. This is equal to 0. This is a conserved quantity. Okay. And what's this conserved quantity? It's an angular momentum, is it? But angular momentum with respect to what? What's the direction of this angular momentum? All right. So we see that this is the angle. So it's angular momentum about the z-axis. Right. So when phi changes, right, when phi changes, Lagrangian does not change. There is a symmetry. So the corresponding angular momentum is conserved. Okay. Corresponding angular momentum is conserved. So it's the angular momentum along the z-axis. That's the angular momentum along the z-axis. Okay. All right. Okay, I think we'll quickly do one more problem or two more. The equation of motion of a system is described by the time dependent Lagrangian. So this was asked, these are previous NET questions. This was asked for the NET JRF exam in December 2014. So the Lagrangian is given. Okay, you are asked to find the equations of motion. It's easy. You just do the calculations, mechanical calculations. It's not very difficult. You just have to be a bit careful. All right. So this such easy problems are also asked. E raised to gamma t half mx dot square minus v of x. Okay. So let's just completely do this. This is easy. Dou L by dou x dot is equal to e raised to gamma t mx dot. Okay, what's dou L by dou x? Dou L by dou x equal to minus dou v by dou x. Okay, so the thing you have to be careful about is when you take the time derivative of dou L by dou x dot. Okay, just take the time derivative of this. But now there are two terms. All right, you first have to, because there's a time appearing here, you have to use the product rule. That's the catch here. So you see that when you differentiate e raised to gamma t, it becomes gamma e raised to gamma t, and keep the second term unchanged. Okay, plus e raised to gamma t mx double dot. Okay, and that's equal to, okay, that let it be there. And oh, sorry, I made a mistake here. Dou L by dou x, there's e raised to gamma t here. Okay, you shouldn't miss that. There's an e raised to gamma t there. All right. And now if you write the equation of motion, you see that the equation of motion for x becomes this. You see that there's e raised to gamma t appearing everywhere. You can just pull it outside. E raised to gamma t outside. So it's gamma mx dot plus mx double dot, okay, minus dou v by dou x is equal to 0. Alright, now there's something multiplied and it's equal to 0, so you can just leave that part. There's also an yeah, that's correct. Okay, so dou L by dou x is minus dou v by dou x, so it means that you will have a plus here. Okay, because the equation of motion is d by dt of dou L by dou x dot minus dou L by dou x equal to 0. Right, so the final answer becomes this mx double dot plus gamma mx dot plus dou v by dou x equal to 0. That's the answer. Okay, do we have that answer here? Yes, that's right. Okay, that's option A, I think. That's correct. Okay, so that's the right answer. Okay, I think it's time to wind up today's class. We'll do a few more problems from this section before moving on to the next one. Okay, I hope you enjoyed the class, and I think I'll give you some exercise problems in your lecture notes. Okay, with the lecture notes I shall include some exercise problems that you can practice. Okay? In the meantime, you also complete the things that we did not do in this. Okay, finding the equations of motion, etc. Okay? So thanks for now. See you in the next class.